What would you do if you needed to power one of the world's largest economies, but had no domestic fossil fuels and almost nowhere to put a wind farm or a solar panel? That's the question facing Japan's energy planners, and their answers might surprise you. Every day, millions of people pass through Tokyo's train stations, and they actually tried harvesting the energy from all those footsteps. East Japan Railway Company installed piezoelectric elements under the tiles at ticket gates in 2006, then expanded the trial in 2008. It made headlines around the world. There's just one problem, and that problem is physics. The 2006 trial ran for nearly 2 months, with around 800,000 people passing through. The maximum daily output was not even enough energy to charge a smartphone. The follow-up in 2008 expanded to 90 square metres of flooring, with a daily kilowatt target of 0.14 kilowatt hours, enough to charge roughly 10 smartphones. Very ambitious. There's no published update on whether they even hit that target, and the project was quietly discontinued. So this specific project was probably never a good idea. But as we'll see in this video, there are plenty of other ideas that Japan is trying that may seem nearly as crazy at first impression. Technologies that most other countries have put in the too hard basket. But the fact is, there are no easy options in Japan. Even the fossil-fueled status quo is hard and expensive. I'm Rosie Barnes, an engineer with a PhD and 20 years experience developing clean energy technologies. Welcome to Engineering with Rosie. Japan's energy problem is unlike any other nation on Earth, and that's largely because of plate tectonics. Japan sits at the collision of 4 tectonic plates, which gave it some of the most dramatic and celebrated landscapes on Earth: volcanic mountains, rugged coastlines, dense forests. But that same geology left Japan with almost no flat land, no coal seams, no oil fields, no gas reserves. The country is geologically spectacular, but energetically challenged. Japan imports 94% of its energy from overseas. For decades, it managed that vulnerability with a massive bet on nuclear power. By 2010, nuclear was supplying about a quarter of Japan's electricity, with plans to push that to 50% by 2030. Then, on the 11th of March 2011, a magnitude 9 earthquake and the tsunami that followed triggered a meltdown at Fukushima Daiichi. Within 14 months, every single one of Japan's 50 nuclear reactors had been shut down. Japan replaced that lost power by burning more imported gas, and electricity prices rose as a consequence. That dependence has only grown more precarious since. The Ukraine invasion sent global gas prices to record highs, and recently the trouble in the Strait of Hormuz has threatened a supply disruption that Japan hasn't faced since the 1970s oil shocks. The case for domestic clean energy has never been more urgent, and Japan is moving in that direction. Currently, renewable energy covers about 25% of Japan's electricity. Solar has grown from 2% of electricity in 2014 to 10% today. But wind is still just 1%, compared to an average of 10% across the other G7 nations. Hydro contributes 8%, but it's close to its practical limit. Japan's near-term expansion plans rely on solar, and much of that will come from rooftop and building mountain installations, because flat land for large-scale ground-mounted solar barely exists. Wind is even harder. Japan has had wind turbines on mountain ridges since the early 1990s, making it one of the earlier adopters of the technology. But away from those ridges, the onshore wind resource is pretty poor. And on the ridges themselves, most are in national parks, and the lightning strikes there are the most powerful on Earth, creating significant operational challenges for turbines. So the mainstream renewables that countries like Australia and China are using to rapidly transform their energy systems simply can't go as fast or as far here. So Japan needs other options. What's interesting to me is that Japan's constraints mean that technologies that might seem like a waste of time elsewhere may actually make sense here because there simply aren't easier alternatives. I've ranked 8 of the options on one criterion only: technical viability. Would this actually work at the scale that Japan needs? These rankings aren't predictions for what I think will happen. They're what should happen in a perfect world where everyone just does exactly what engineers tell them to. That's a joke, by the way. A funny engineering joke. Some of these technologies might surprise you. Some of them shouldn't probably have ever made it past the back of the envelope. And we're going to finish this video on the option that scores best on every technical measure. The one that would genuinely solve Japan's energy problem. The one that will almost certainly never happen. So let's start with the status quo. After Fukushima, as reactor after reactor went offline, it was gas that stepped in to fill the gap. Liquid natural gas, LNG, now accounts for about 33% of Japan's electricity, and Japan is the world's second largest LNG importer. It's not a clean solution, but it's not worthless either. Gas plants are flexible compared to Japan's other major source of generation, coal. Gas can ramp up and down quickly to compensate for the variability of solar and wind, and that matters a lot in a grid as fragmented as Japan's. As renewables grow, gas can support that transition, hopefully, rather than obstruct it. But it's fully imported, it's expensive, it's a fossil fuel, and it has no future as a long-term strategy. That adds at number 6 on my list. So if it's the fact that it's a fossil fuel that's the problem, what about replacing it with cleaner imported fuels? Japan has 2 answers to that question. Next up is importing hydrogen. The idea is to produce green or blue hydrogen overseas, liquefy it, ship it here, and then convert it back into electricity. It's essentially LNG rebranded, but with much worse physics at every step of the chain. I made a full video on an Australian-Japanese trial of this, but the short version is that the efficiency losses from liquefying, shipping, and regasification stack up to something that is very hard to justify. The cost estimate from Japan's Ministry of Economy, Trade and Industry, METI, confirm it. Hydrogen is the most expensive electricity generation option in their entire modelling. The original Australian trial should have killed this idea. Instead, trials are continuing and investment is flowing in. Hydrogen for grid electricity is last on my list, and I'd be surprised if it ever moves up. But what about if hydrogen were just easier to ship? Well, that brings us to ammonia. Unlike hydrogen, ammonia already has a global shipping infrastructure. We've been transporting it for decades for fertilizer production. It's liquid at minus 33 degrees Celsius compared to minus 253 for hydrogen. So the energy and the logistics are a lot more manageable. That's a real advantage. The problem isn't shipping. It's what you do with it when it arrives. JERA ran the world's first large-scale demonstration of 20% ammonia co-firing at their Heikkinen coal power plant in 2024, and Japan is intending for this to be part of its decarbonisation pathway. But 20% ammonia co-firing only reduces life cycle CO2 emissions by around 12% when using blue ammonia, because upstream emissions from producing the ammonia eat into the savings. And going beyond 20% isn't a matter of just gradually adding more ammonia. Beyond that 20% threshold, you need different burners, major boiler upgrades, larger storage, and more advanced NOx control. So the 20% isn't a stepping stone to 100%, it's a cliff edge requiring completely new equipment afterwards. Ammonia for electricity production is only a tiny bit cheaper than hydrogen, and the deepest problem is that building an energy strategy around ammonia co-firing means keeping coal plants running for another 20 years or so. So ammonia is number 7. Importing fuel in any form is expensive, insecure, and in my opinion, neither hydrogen nor ammonia have any business being used to generate grid electricity. I expect that the reason Japan pursues it anyway is that diversified imports spread geopolitical risk. But diversified imports are still imports. The only strategy that actually solves import dependency is domestic generation. Japan tried that once before with a massive bet on a single technology, and it almost worked. We're talking about nuclear power, and it's the option that probably generates the most emotion in Japan. As I mentioned in the intro, nuclear was providing a quarter of Japan's electricity by 2010, with government plans to push that to 50% by 2030. Then, on the 11th of March 2011, a magnitude 9 earthquake triggered a tsunami that overwhelmed the seawall at the Fukushima Daiichi plant, knocking out backup power and disabling the cooling systems for 3 reactors. Over the following days, all 3 experienced meltdowns. Around 160,000 people were evacuated from the surrounding area, many of whom never returned. The evacuation itself, carried out rapidly and in chaotic conditions, caused over 2,000 deaths among elderly and vulnerable people moved from hospitals and care homes. Some communities remained off limits for years. Fukushima was a serious nuclear accident, but it was not actually a radiological disaster. There were no deaths from radiation exposure. In a strange way, Fukushima validated something important, that well-designed safety systems can prevent deaths even when the worst happens inside the reactor. 3 meltdowns and the containment largely held. But the margin was uncomfortably thin, to say the least. Hydrogen explosions damaged the reactor buildings and came very close to preventing workers from accessing the site to maintain cooling. A slightly worse set of conditions, a slightly larger wave, a slightly longer power outage, and we would be talking about a very different event. To me, Japan's decision to shut everything down and demand higher safety standards made sense. But so does the decision to rebuild their nuclear capacity after improving safety. Today, 15 reactors are back online, generating 9% of Japan's electricity. The government wants 20% by 2040, which would require up to 30 reactors operating simultaneously. But of the remaining 32 operable reactors, only 3 have regulatory approval to start so far. So the pipeline is moving very slowly. And even if Japan hits that 20% target, obviously nuclear alone won't solve the entire problem of Japan's electricity grid. It's a partial answer, so I'm putting it at number 4. The challenges that make nuclear so nerve-wracking here, the ring of fire, the earthquakes, the subduction zones, actually created the opportunity for our next technology. Japan is sitting on the world's 3rd largest geothermal resource. 23 gigawatts of potential energy that can be economically extracted, bubbling away underground. And Japan is barely touching it. Japan is only using 3% of what is economically viable. The reason is largely political. Onsen hot spring resorts are culturally and economically important in Japan, which I understand. I have enjoyed many onsens myself. But onsen owners have successfully blocked geothermal development for decades over fears it will affect their water supply. The science doesn't really support that, but it's perception that matters here. The government's 2030 geothermal target is 1.5 gigawatts, which would be a tripling of current capacity in just 4 years. Japan has been adding capacity at roughly 20 to 30 megawatts per year, so to hit 1.5 gigawatts by 2030, they need to be adding around 150 megawatts per year, which it doesn't seem like they're on track to do. This is as much of a people issue as an engineering issue, which is why I travelled to Tsuchiyu Onsen in Fukushima to find out more, and I will make a full video on that, so watch out for that one. I put geothermal at number 3 because its potential is probably less than 10% of Japan's grid. A whole lot more than the current 0.3%, but never going to be the major chunk. So with geothermal, the resource is there, the technology works, and yet the politics means Japan is barely scratching the surface of what's sitting underneath it. But what about above the surface, specifically above the ocean? I mentioned at the start that onshore wind is tricky for Japan to scale much further. Fixed bottom onshore wind is also fairly limited because Japan's coastline drops steeply into very deep water almost immediately offshore. For the majority of Japan's wind energy potential, they'll need floating wind, where turbines are anchored to the seabed rather than fixed to it. The technology exists and it's being deployed in small numbers, mostly in Europe. Japan has one floating wind project in development. Principal Power's Windfloat Japan is set to have a capacity of 5 megawatts when it's finally installed. But for now, floating wind remains significantly more expensive than fixed bottom. And the engineering challenges around dynamic cables, mooring systems, and installation in deep water are real. The potential is enormous, 424 gigawatts by some estimates, but is a technology that still needs to prove itself at commercial scale before it can carry the weight Japan needs it to carry. Floating wind is one of my pet topics, but I won't talk about it too much here because I want to make a longer video talking about some of the cool things that Japan are already doing with floating wind. Anyway, floating wind is number 2 on my list. From above the water to just on top of it, let's move to floating solar. And this is one that Japan invented themselves. There are nearly 7,000 installations across the country, mostly on inland reservoirs where land is too scarce for ground-mounted solar. But there's a problem: typhoons. In 2019, Typhoon Faxai destroyed the majority of the panels at the Yamakura Dam floating solar plant in a single storm. 2 weeks later, a second installation in Kyushu was destroyed by another typhoon. Floating solar on open water is extremely vulnerable, which is why it's largely confined to sheltered inland reservoirs, capping the total potential at somewhere between 15 and 30 gigawatts. The other problem is the grid. Japan's electricity system is split into 10 regional utilities with limited interconnection between them. A typhoon that wipes out generation in one region can't easily be compensated for from another. That's a grid architecture problem as much as it is a floating solar one, and it affects all of Japan's weather-dependent generation. I'm putting floating solar at number 5. So Japan's best domestic options, floating wind, geothermal, and floating solar, are all viable in an engineering sense, but each of them are constrained and probably none are developing as fast as we'd like. But there is one technology solution that isn't constrained in capacity and would be pretty fast to roll out too. It's sitting right there across the water, and it will almost certainly never happen. I'm talking about a subsea HVDC interconnection to one of Japan's neighbours, so that'd be either Korea, China, or Russia. Now, I mentioned before that Japan's domestic grid is fragmented. It's worth looking into that a bit before we explore the possibility of expanding it internationally. Fun fact, Japan's east and west grids run on different frequencies, 50 Hz in the east and 60 Hz in the west, a legacy of buying generators from different European countries in the 1880s. So it's difficult to even move electricity between Hokkaido and Tokyo. The HVDC interconnector that bridges them only came online in 2021. Now imagine connecting that grid internationally. The Japan Sea routes to Korea and Russia have been studied. Seabed depths are very manageable, most viable routes staying below 400 meters, with cable lengths under 600 kilometers, comparable to existing European interconnectors. Active fault zones and fishery rights require careful route planning, but they're not technically prohibitive. Investment costs estimates range from 200 to 600 billion yen, modest compared to Japan's annual transmission infrastructure spend of 1,800 billion yen. The engineering case is not outlandish. As I discussed at depth, pun intended, in a recent video, subsea HVDC is proven technology. The distances and depths for a Japan-Korea or Japan-Russia connection are very manageable. The problem is the politics. Connecting to China, which has the largest renewable energy surplus in the region, means navigating unresolved territorial disputes, deep historical grievances, and active geopolitical friction. Korea is more feasible politically, but represents a smaller and less diversified supply. Russia is also now essentially off the table. So a subsea interconnector is number one for technical feasibility, but obviously not political. We started on that station floor in Tokyo, running the numbers on a technology that made headlines but never made sense. The difference between Japan's current energy options and that piezoelectric floor is that these options do make engineering sense, at least most of them. But all of the technologies I've discussed here are hard. The fact is that Japan has nothing but hard options when it comes to energy. But Japan also has a fantastic engineering tradition, and I have spoken with many amazing engineers and other energy professionals during my visit here. And I'll tell you what, they are excited. Most of the engineers that I know, myself definitely included, get totally energized by a hard problem. It is a lot more fun working on something that has never been done before, that you don't even know if it's possible, than just rolling out more and more of the same easy projects. The fact is that Japanese engineers will get the chance to develop solutions that other countries won't bother looking at because they have simpler, cheaper solutions available. Japan already came up with floating solar because they didn't have many land-based options. They're now developing underwater construction technologies to help speed installation of floating offshore wind and bring down costs that way. And there will be others. If successful, these kinds of technologies will find applications elsewhere and could become the next big export industry for Japan. There is a very long list of people who helped me with this video in some way, especially Nkosi, who invited me here to speak at their systems engineering event. So thanks to all of them. Thanks also to the Engineering with Rosie Patreon and YouTube members. They get early access to new videos, chat on our exclusive Discord server, and get a say in future video topics. But most members are really here just because they want this kind of content to keep existing. If that sounds like you, you can join at this link. Thanks for watching, and I'll see you in the next video.